So welcome everybody. Today we just have 1 hour. In the last talks, we discussed this issue of monotone systems and cooperative systems. Which are, of course, very closely related. These topics are very closely related. And I wanted to add just one remark about this issue of monotone systems and cooperativity before we return to the issue of sensitivity of the RFM equilibrium. This is the main topic today, but just I wanted to say something. So if we have a system, a linear system, we said that it is cooperative if A is Metzler, and it is monotone if for any two initial conditions, the solutions preserve the ordering between the initial conditions for every point t. By the way, I don't remember if I emphasized this enough, but you always compare the two solutions at the same time instant t. Okay, you don't compare this at t1 and this at t2 because they can change. But you always compare them at the same time, but you can do this for any time t as long as you compare them at the same time. So this is monotonicity, this is cooperativity, and we gave a theorem, and we actually, I think, proved it, that said that for this linear system, monotonicity, if and only if, cooperativity. And this is very useful because we don't need to know A explicitly. Sorry. We just need to look, what does it mean, Metzler? We just need to look at the off-diagonal entries and know that they are not negative. They have to be positive or zero. Now, in many systems, you don't really know the entries here. Perhaps there is some uncertainty or the parameters are not known explicitly, but you know somehow that the state variable number 1 has a positive effect on state variable number 2, and maybe state variable number 1 has a negative effect on state variable number 1. So you know, in many systems, in systems biology, but I'm sure that also in other fields, maybe you don't know the complete details of the connections, but you know if they are inhibitory or excitatory. So this will correspond to a plus or a minus, and for this condition to hold, you just need to know the signs. So this is very useful. But there is a delicate point here, and the delicate point is as follows. Suppose that this is Metzler. Suppose that A is Metzler. So the system is cooperative and monotone. Now I define a new state variable fix some n by n matrix T, which is non-singular or invertible, and define a new state vector Z is T multiplied by X. Then the dynamics for Z is Tx dot, which is Tax, which is Ta_T minus 1Z. This follows immediately from the definition of Z. X dot is just Ax, and X is T minus 1Z. Now, even if A is Metzler, this does not have to be Metzler, does not have to be Metzler, because when you multiply it by T and T minus 1, it can change the signs. It can easily change the signs of the entries, and in particular, the off-diagonal entries. So from here, when you look in this coordinate system, you can prove cooperativity and monotonicity and all the results that we know. From here, it will not be evident. So it is important to understand that this condition for cooperativity is not invariant under a coordinate transformation. The coordinate transformation may spoil the Metzler property, and it also works the other matrix T, so now this is not Metzler perhaps, but if you can find an invertible matrix T such that this is Metzler, suppose that you can find this. This is possible because again, T and T minus 1 can change the entries and the sign of the entries. Then you know that this system is cooperative and therefore monotone, and you can conclude all kinds of results for Z. Of course, all this also holds in the nonlinear case, where you look at the Jacobian and you want it to be Metzler, and again, you can do a coordinate transformation. So if after a coordinate transformation you see that it is Metzler, then the system is cooperative, then you can apply all the results like Giag's theorem to deduce something on the Z system, and then immediately you get results on the X system, because when you just change two systems by an invertible coordinate transformation, it's not really a change. You just somehow twist the coordinates, maybe you scale them or you do something, but if you can prove something for this system or for this system in the Z coordinates, then, for example, that everything converges to the unique equilibrium, then of course it holds here as well. So when checking this cooperativity, you have to be a little careful in the sense that maybe it does not look cooperative, but perhaps there is some coordinate transformation that will make it cooperative. For the RFM, we are lucky, and when we look at the Jacobian of the RFM, it is automatically Metzler, automatically cooperative. But the theory applies to a broader class of systems. If you can find a coordinate transformation such that under the coordinate transformation, the Jacobian is Metzler, then everything will work. Okay, I just wanted to explain this because it is important to understand that sign conditions like this are not invariant under a coordinate transformation. So this is a bad side and a good side. The good side is that maybe we can find, if we are lucky, a good coordinate transformation that will take a system that does not look cooperative into an equivalent cooperative system. Okay, I now want to talk about sensitivity of the RFM. No. Sorry. Spectral representation of the RFM steady state. Okay? So we started talking about this in the last lecture, and now I want to speak about this more because this is a very useful and important property, and I will describe some applications of this, but I think that there are more, and maybe this can be an interesting research topic to think about more applications of this spectral representation. So the idea was as follows. We have a set, we have an RFM, and the RFM has a set of n+1 positive parameters, which are the initiation rate, the exit rate, and all the internal translation rate, just like in TASEP. And we know that there is a unique equilibrium and that any solution converges to this unique equilibrium for any initial condition in our state space, which is the n-dimensional unit cube. And moreover, the convergence is exponential with an exponential rate. This can be proven using contraction theory. We already proved it. So it means that after a relatively short time, we are very close to E, and by understanding the behavior at E, we can understand the behavior in general. So it is important to understand E. Now we have a set of nonlinear equations characterizing E, but this set is not very useful. I claim that it is not very useful. There is a much better representation, and we spoke about this. Last week, in the last lecture. You take a matrix of dimension n+2 by n+2. You build a matrix of dimension n+2 by a+2. How? You put zeros on the Venn diagonal. You put these lambda i's scaled to minus 1/2, they are positive numbers, so this is well defined in the super diagonal. And you also put this in the sub-diagonal. And all the other entries are 0. Now this matrix has non-negative entries, and it is irreducible, so it follows from the Perron-Frobenius theorem that there is a vector V with all entries positive, and there is a positive eigenvalue sigma, so that sigma is also the dominant eigenvalue, so that this holds. We know that there is a positive eigenvector corresponding to an positive eigenvalue, eigenvalue, corresponding to an eigenvector V, which is component-wise positive. Let's look for a moment about what this means, what this equation, the matrix multiplied by V is equal to sigma V. What does this mean? So let's write here V1, V2, up to Vn. I want to relate this to the RFM steady state. So we will do this in stages, slowly. So let's look at this equation. This equation simply says that sigma is a real eigenvalue, positive, this is from the Perron rule, corresponding to a positive eigenvector, again, from the Perron-Frobenius theorem. So let's look at these equations and write them down. I don't want to erase this, so I will write the equations here. The first equation gives us lambda 0 minus half V2 is equal to sigma V1. This is from this row multiplied by this and equal to this. The second row gives us lambda 0 minus half V1 plus lambda, what will be the second equation? Let me see. Okay, so I write it already in, I have a lot of equations. So I write all the equations. This was the first equation. Now I have a lot of equations in the middle. And then I have the last equation. The last equation is lambda n minus half multiplied by Vn minus 1 is equal to sigma Vn. This was this equation. Sigma n minus half, this is multiplied by this one, Vn minus 1 is equal to sigma Vn. And all the equations in the middle, if you look at them, I claim that I can write them like this. So here I have n equations, and this is the first equation and the last equation, in total n plus 2 equations, because this matrix is n plus 2 by n plus 2. Sorry, I made a mistake here. Here it should be n plus 2, because everything is of dimension n plus 2. So I just wrote the equations explicitly, and if you check, you will see these equations. Why? Because here you have 0, and here you have lambda 1 minus half. So you just write the equation, all the rest are zeros. So lambda half will be multiplied by V1, and this will be, lambda 1 will be multiplied by V3, and all this gives us sigma V2. So I just wrote the equations explicitly. These were the equations from AV equal to sigma V. I erase now this because I need the space, and I already wrote the equations here. By the way, as always, if there are any questions, please let me know. Aditi asked me yesterday if in Gian theorem we need to assume convexity. That was a very good question, because I checked and we don't need to assume convexity. So I fixed this in the lecture notes.
Okay.
Thank you very much. Thank you very much, Aditi.
And so, Michael, in the last equation also, then Vn plus 1, I think it should be there, and Vn plus 2.
Yes. Sorry. You're right. Thank you very much. It's like this. Thank you. Because the vector goes all the way to n plus 2. Thank you very much, Aditi. So you see, My experience with my graduate students is that those that correct me during my lectures were eventually the best graduate students I had. So please don't hesitate. Okay, so I write these equations, and now I want to manipulate a little bit these equations, and I want to show you that I can get the equations for the equilibrium, the equations describing the equilibrium in the RFM. So let's define di as lambda I minus half vi plus 2 sigma vi plus 1. This is well defined because all the entries of the vector v are positive. All the entries are positive, and this is positive, and this is positive, so it is well defined and even positive. This is a definition. And I do this for every I from 0 to n. And the motivation for this is that all equations, if I divide by Vn plus 1 here, you see, I get this structure. And if I divide here by V2, I get this structure. So I want to divide these equations by some VIs and then get the equations in terms of the new notation or the new variables di. So now let's see. With these definitions, what do I get from the equations? D0 is lambda 0 minus half divided by sigma V2 divided by V1. Yes, I just substituted the I equal to 0 here in every term. But now look at this first equation. From this first equation and this definition for D, I get that D0 is 1. Look at this equation. This is just sigma. If I divide by sigma V1 on the left, I divide by sigma V1 on the left, I get D0. And on the right, I get 1. So the first equation, it's better to represent it in some sense using the DIs, because using the DIs, I just get the equation D0 equal to 1. Now I look at this equation. These are n equations. And if I look at these equations, I can write this equation in this form. If you check, you will see that I get exactly this equation. Why? I divided everything by sigma vi plus 1. I divided everything by sigma vi plus 1. So here I get this divided by sigma vi plus 1. This is what I wrote on the left. Here I get exactly di. After I divided by sigma vi plus 1, this term, I get exactly di, and I can shift it to the right, so I have minus di. And here, when I divide it by sigma vi plus 1, I get 1. So this is exactly the equation I get from all these middle equations. And here I is between 1 to n, or to n. Yes? Is it clear what I did here? Maybe I should have done it in 2 steps. Anyway, I divide by sigma vi plus 1. I divide by this term all the equations. So here I get 1. Here I get this term divided by sigma vi plus 1. I wrote this. And here I get just a di. This is just di. When I divide by sigma vi plus 1, this is just di. And I shift it to the right-hand side. And from the last equation, I get dn equal to dn equal to sigma minus 2 divided by lambda n. Let me check that I didn't make a mistake here. So again, I divide by sigma vn plus 2. Let's divide by sigma vn plus 2. So we get lambda n minus half vn plus 1 divided by sigma vn plus 2 equal to 1. Let me see that I wrote the equation correctly. Yes, I wrote the equation correctly. And now this is probably dn. This is, sorry, maybe there's a typo. Okay, so we check now. So this is just no, this is not dn. Blah, blah, blah. Okay, so let me see. dn. What is dn from here? Let's check what is dn. dn is sigma n minus half sigma vn plus 2 vn plus 1. This is dn from the definition of all the di's. And here, okay, so I need to, so I need in this equation sigma vn plus 1. How do I get dn? Let me see. Let's divide first of all by vn plus. Let's divide by vn plus 1. I divide both sides by vn plus 1, so this disappears. And now I get, okay, so I get here lambda n minus half. That's okay. I just divided by vn plus 1. Now, let's multiply by lambda n minus half in both sides. Lambda n minus half in both sides. And then here I get lambda 1 minus 1. I multiply by lambda n minus half in both sides. And let's divide by sigma in both sides. So here I need to divide by sigma. First of all, I divide by sigma. And then I divide again by sigma. Then here I get dn. And here I get sigma minus 2 divided by lambda n. That's exactly what I wrote. So these equations, when I define the di's, I get this set of equations, an explicit expression for d0, an explicit expression for dn, and some recursive expression or expression for di. And now, why is this useful? Let's take this equation and denote it by 5.6. This is how it is noted in the lecture notes. Let's divide it by di minus 1. And then we also simplify a little bit. And then we get the following. Using the definition of the di's, after we multiply this equation on both sides by di minus 1. So I multiply here by di minus 1, I just get this. And when I multiply here by di minus 1 from this equation and I simplify, I just get sigma minus 2. And this is very useful. Okay, first of all, recall that sigma is positive. Since sigma is positive, we conclude that every di, and di was also positive, so we conclude that every di must be in 0, 1. The definition of the di doesn't show this immediately, but when we look at the equations and we write them, we get this equation that all of them are equal to the sigma to the power minus 2. And because this is positive, this must be between 0 and 1. Very good. And now, let us write all the equations that we got here, okay? Sigma minus 2 is equal to what? First of all, I write here for I equal to 1. I get sigma 0, d0. This is for I equal to 1. Sigma 0, d0, 1 minus d1, and 1 minus d0, sorry. 1 minus d1. Yes, okay. This was this equation for I equal to 1. Let's check again. For I equal to 1, this is sigma 0, this is d0, this is 1 minus d1. Very good. Now d0 was 1, so I erase it. Just write this. Because d0 we already concluded from this equation that it is equal to 1. Now let's look at what this equation gives us when we plug in I equal to 2. Then we get lambda 1, d1, 1 minus d2. And we continue like this until we get here lambda n minus 1, dn minus 1, 1 minus dn. And in the last equation, we get lambda n dn. This is from this equation. Lambda n, yes, lambda n dn is equal to sigma to the power of minus 2. lambda n dn from this equation is just sigma minus 2. Now we have a very nice situation. Why is this a nice situation? Because remember, what were the equations of the RFM? The equations for the steady state of the RFM. The equations were like this. Lambda 0, 1 minus E1 is equal to lambda 1, E1, 1 minus E2, equal to lambda 2, E2, 1 minus E3, lambda n, En. These were the equations for the RFM steady state. And we know that there is a unique solution for these equations, a unique solution where every EI is in 0, 1. We know this. And now look at these equations. These are exactly the same equations, but now with variables called D1, D2, D3, and so on. Exactly the same equations, and we know that every DI is between 0 and 1. And because there is a unique solution of the RFM steady state equations in 0, 1, and because these are exactly the same equations, but everywhere instead of EI, I see a DI, and the DIs are between 0 and 1, we conclude that this DI that we defined here is just the equilibrium point EI of the RFM. This is the conclusion, because the EIs and the EIs and the DIs satisfy exactly and the DIs are in this range. So the conclusion is that if I take my matrix and I calculate the Perron eigenvalue and the Perron eigenvector, and I define DI like this will exactly be EI in the RFM. And this is the theorem I gave you last lecture. It said take this big matrix, calculate sigma in V, and EI will be this. And actually we get a little more. We also got that lambda n En, this is lambda n Dn, but Dn is En, is equal to sigma to the power minus 2. So this is the steady state production rate. The steady state production rate is exactly the Perron root of the matrix to the power minus 2. So you can also calculate the steady state production rate immediately by taking the Perron root of the matrix and raising it to the power minus 2. So the idea again is that you take this matrix, you write the equation for the eigenvector corresponding to eigenvalue sigma, you do some manipulations, not very complicated, just a little bit of algebra, and you find that after you define di, has exactly the same set of equations of the EIs, and because there is a unique solution in 0, 1, every DI is just a EI. And that's it. So questions about this? This completes the proof that you can obtain all the information about the RFM steady state from this spectral representation in the matrix A, from here. Questions, please.
Okay, Michael. So we had a matrix and we derived a spectral representation for the RFM. My question is, since we don't know about the structure in the first case, like we know in here, so what the steps we need to follow to derive the spectral representation for any another model or differential equation?
Well, that's a very good question. We are very lucky in some sense in the RFM that we can take this set of equations and transform them into the equations relating the eigenvalue and the eigenvector. It's a very interesting question. What you ask is, what other more general models, suppose that I take some other more general model than the RFM and I get some other set of steady state equations, when can I manipulate them to eventually get a spectral representation? The answer is I don't know. I don't know. It's a good question, but I don't know. There are some cases where we were able to do this. There is something called the RFM on a ring. The RFM on a ring, when the particles leaving the last side go back to the first side. So this corresponds to a circular RFM. And in this RFM ring, we were also able, for example, to find a spectral representation. And there is another model where we were able more or less to do this. But the general question of when, why is it possible, I don't know the answer. I don't know the answer. The way we go to it is that I spoke about this briefly in the first lecture. If we define R as lambda n equal to En, the steady state production rate, then we can get a continued fraction expression for R, and there is a close connection between continued fractions and the eigenvalues of tridiagonal matrices. So we knew more or less what to look for. But how to generalize this, that's a very good question. And define the most general model where you can do this, I don't know.
Okay, thank you.
Thank you. Okay, so let me summarize.
Hello, sir.
Yes, another question, please.
Yes, sir. Good evening, sir. Sir, basically, I want to ask that what is the relation between, for example, the spectral representation from biotechnology point of view?
From what point of view, I'm sorry?
Biotechnology point of view, like ribosomes.
Okay. Yes, yes. Okay, so I will speak soon. Now, the next topic is applications.
Okay.
Implications of the spectral representation. I will give a few implications, and maybe there are more. And then, of course, I will answer this question, I hope, in the next half an hour or so, and maybe also tomorrow. So I will speak now about implications. So that's a good question as well. Let me just write down a summary of what we showed to take, because I just want it written as we speak about the implications. To take the RFM is n plus 1 rates. You build this matrix, I won't write it again, but you have here the lambda i's and you have here the lambda i's ordered. And you take out the eigenvalue, the Perron root, and the corresponding eigenvector, and you know all the entries are positive. And then EI in the RFM will be equal to lambda I to this DI. So I write it now. VI plus 2 divided by sigma VI plus 1. So this is what we concluded. And also, lambda n En, which is the steady state production rate, is just sigma to the power minus 2. Good. Now I want to talk about implications or applications of this spectral representation. So, first of all, we are very lucky. Why are we lucky? Because in a general nonlinear dynamical system, you have maybe an equilibrium. It's very hard to represent the equilibrium in this way. Here we have a lot of structure, and we will see soon how we use it. Not just by looking at the equations where the derivatives are zero, which are not very helpful, but eigenvector of this matrix, which we denoted by A. Now, if you remember, when we spoke about, so first application. So this is, okay, so let me describe and then I will give it a title. I don't know yet what is the title. You remember that when we spoke about contraction, we spoke about the L2 norm of a vector. This was the L2 norm of a vector, and we spoke about the induced matrix norm. The induced matrix norm I told you that what do? You multiply A transpose by A. This is a symmetric matrix, so all the eigenvalues are real. You take the lambda max, the maximum on all the real eigenvalues, and this will also be non-positive because this is a non-negative definite matrix, and non-negative. This will be non-negative, so you can take the square root. This was the induced L2 matrix norm. Now, matrix norms, vector norms, also always satisfy the triangle inequality, and you can show using this that matrices also satisfy, matrix norm also satisfy a similar inequality. Okay, so you know in 0 and 1, inside 0, 1, and actually look at RA plus 1 minus RB, the norm of this matrix. I fix some number R between 0 and 1, and I look at this combination. So this is like a linear line between A and B. From this inequality, I know that this will be smaller than RA plus 1 minus RB, because this is just the sum of two matrices, okay? This is one matrix, and this is another matrix. So when I sum up two matrices, I know this is called the subadditivity property. So this subadditivity property holds, and I also know that for norms, I can take the absolute value of R here, and I can take the absolute value of minus R here, but R is between 0 and 1, so I don't have to take absolute value of R and 1 minus R. I can just take R themselves and 1 minus R. In general, I have to take the absolute value. When I scale a matrix by R, the matrix norm scales by the absolute value of R, but here R is non-negative, and also 1 minus R. So the conclusion is, what is the conclusion from this calculation? The conclusion is that the L2 norm of a matrix is a convex function. Right? A function where if you take this linear sum of A and B, it is smaller than this. This is exactly the definition of convexity. So, and this holds everything I wrote there actually holds for any matrix norm. But we are interested in the L2 matrix norm. Now let's look for this matrix. This matrix is already symmetric. Now we speak about our specific A. This matrix is already symmetric. So here we just get A squared. And also all the entries are, the lambda max, of course, again, from Perron theorem will be positive. So actually this tells us that when we take A squared, we get lambda squared, and then we take the square root. So this is not just lambda max of A, but this is just sigma. So sigma is equal to the L2 norm of A. Sigma is the L2 norm of A, and the L2 norm of A is convex. So the conclusion is, from this argument, that sigma is a convex function of the matrix and is a convex function of the entries of A. Can you see when I write on the lower part of the board? It's okay?
Yes,
Yes, sir, it is okay.
Okay, good. So sigma is a convex function of the entries of A because sigma is just the L2 norm, and the L2 norm is always convex. Now, lambda and En is sigma to the power of -2. So lambda and En, or R, is a concave function of the lambda i's. The entries of the matrix are just the lambda i's, yes? What are the entries of A? No, sorry. Concave function, okay, it's better to say of the lambda i's to the power minus half, because these are the entries. The entries are the lambda i's to the power minus half. So the steady state production rate, because sigma is a convex function of the entries of A, the entries of A are just these lambda i's to the power minus half, and here we get sigma to the power minus 2. This means that R is a concave function of the lambda i's of the entries, which are the lambda i's minus half. So what does this mean? So, okay, so let's give this a name now. This is concavity of R, the steady state production rate. And this means the following. Because it is concave in the lambda i's to the minus half, this means that R I mentioned this in the introductory lecture, so let me just make sure that I'm right. This means the following. The problem so the problem to maximize R subject to lambda I non-negative and sigma lambda I bounded by B is a convex optimization problem. Okay, first of all, even before that, what this means is the following. If I plot R as a function of the rates, let's assume I have just two rates so I can make the picture, then R will look like a concave surface. This is what it means. Just a minute, maybe I made a mistake here. Maybe this is T convex, and then R is convex in these, and because of that, it is concave in the rates. Let's see. We said, okay, I'll check this and correct this in the next lecture, because I don't remember right now. But anyway, I claim that it's not difficult to show that R will be concave in the rates. So R will be concave in the rates, not in the lambda i's minus half. I think it is concave. I think it is convex in the lambda i's minus half, and because of that, it is concave in the lambda i's. So it will look like this. And then the problem of maximizing R, maximizing the steady state production rate, subject, first of all, to what constraints? First of all, we know that all the lambda i's can never be negative. So if we just take this constraint, I claim that the solution will be to take all the lambda i's to infinity, because as we increase the lambda i's, the steady state production rate can only increase. So it doesn't mean anything. But assume that there is some budget B, there is a total budget, and you can you constrain your total budget, the total budget that you can spend on your lambda i's is limited by B. Then this is a meaningful optimization problem, and because R is concave in the lambda i's, it's a convex optimization problem, which means that there are very efficient numerical algorithms for calculating the solution of this problem. So in terms of systems biology, I'm not sure how relevant this is, but imagine that you are building now an evacuation corridor. This evacuation corridor, you can divide it into several sites because of the geometry. You can divide it into several sites, say 1, 2, 3. And you can come up with rates here from 1 to 2, I think this is lambda 1, and from 2 to 3, this is lambda 2. So when you build this corridor, this evacuation corridor, the geometry and the width of the sections will determine the rates, lambda 1 and lambda 2, that tell you how easy it is to move from one section to the Now imagine that you model everything using the RFM. You model the flow here using the RFM, and then you know that if you wait long enough, you will converge to this steady state production rate, R equal to lambda n En. We know this, and this will happen exponentially. And you want to maximize the steady state flow. That's a natural requirement from I need to connect the power. That's a natural requirement from an evacuation corridor. And then the question is, and now I have some limited budget, okay? I cannot make the corridor infinitely wide because this will cost too much money or because I have other constraints. So under the constraints, maybe I can model them in this form, as I wrote here. I have some kind of total budget on all that I can waste or spend on the total, in total on all the lambda i's. And then this makes sense. This optimization problem makes a lot of sense. And then it will give me some conclusion, okay? You need to put some value here and some value here and some value here, I don't know, to get the best possible configuration. And by the way, I can, of course, scale things here. I can take any set of positive weights, omega I, and this will still be a convex optimization problem. This means the weights mean perhaps that here I have, for some reason, I can invest more, I can increase this more, but here I'm more limited, I can increase this less. So I can somehow model this using these weights. And even under the weights, this problem can be easily solved numerically. Actually, I think we can also show that it has a unique solution. And this can be useful. Again, I'm not sure about system biology, but when you come to design a highway or you come to design an evacuation corridor, I think this can be useful. So this was one application. The second application is even simpler. We had all these equations for the RFM steady state. This is before we came up with the spectral representation. So this was the first application. But actually calculating EI from here is very complicated. Why? You have to transform this into a polynomial, say, in En. This is equivalent to a polynomial in En. And if n is large, imagine that n is large. So in a model for translation, we can certainly think about something like 500 or 1,000 sites, and maybe more. So n is large. And then you will translate this to a polynomial in En, but it will be a high order polynomial. I don't know exactly the order, but certainly a few hundreds, if n is 500, say. And then you need to calculate En from this polynomial. There will be a lot of solutions because when you solve a high order polynomial, there will be a lot of solutions. And from En, you can just calculate En minus 1 to E1. We already spoke about this, but you have a lot of solutions here. Only one solution will give you that all the EIs are between 0 and 1, but you don't know how to find this solution in advance. So you have to try all the solutions, solve this equation. First, you calculate all the solutions of En, then you solve this equation and you introduce errors. I don't know exactly how the errors in En propagate to errors in the other state variables. And you end up with something very cumbersome and not numerically stable. On the other hand, here, so the topic is numerical computation of E. On the other hand, here, there exist well-known and efficient algorithms for computing the eigenvalues and eigenvectors of a tridiagonal matrix. Because matrices and their eigenvalues and eigenvectors plays such an important role in many fields of mathematics, people came up naturally with algorithms that are useful in the sense that they are relatively quick. You don't need to do too many operations, and also the errors, you have control on how the errors propagate, and the errors are not too large. So you can calculate the EIs and you can calculate the VIs, relatively small errors, and from this immediately get the EIs. Okay, here it's very, very complicated to do this, but here, once you have the spectral representation, you can use known algorithms and known results on how to do this. So the first application was the fact that R is concave, and then the maximization problem is easy to solve. It's a convex optimization problem. The second E. Now, if I'm not mistaken, we have only about 8 minutes. So I will just say something about another application. I will not start the computations. I will do this tomorrow. But the next thing I want to know, naturally, is the sensitivity of E to a change in some lambda I. So I have my rates, lambda 0 up to lambda n, and they induce some steady state value. And now let's say that I change lambda 5, I add an epsilon to lambda 5. All the other rates remain the same. And this induces a new equilibrium point. Let's mark it with E bar because it's different now. I change one of the rates. And naturally, I would like to know how E changed into E bar. So again, here it's very complicated because it's not clear at all if I change lambda, one of the lambda i's here, how it will affect all these equations. But here it becomes a classical problem in matrix theory. When you change one of the entries of the matrix, how is the Perron root, or how do the eigenvalues and eigenvectors change? That's the question. That's a classical question in matrix theory, and from this you can get interesting results telling you what happens when you start to change one of the lambda i's. We already spoke about this a little bit when we spoke about the comparison principle. There we increased lambda 0 and we showed that this can only increase E. But what happens if you change lambda 5? It's not completely clear. And from the spectral representation, certainly it's not clear from here. Lambda 5 appears here somewhere, and you change it. But what does it mean to all these, the solution of all these equations is not clear. But if you change it here, we will see in the next lecture tomorrow that we can use known methods for the sensitivity analysis of the eigenvalues and eigenvectors of a matrix to deduce how E will change when we change one of the lambdas. Okay, so we have 5 more minutes, but I think it's, I don't want to start doing all the computations because then I'll get stuck after 5 minutes. I prefer, if it's okay with you, to allow now 5 minutes for questions, and tomorrow we will start this topic of sensitivity analysis using the spectral representation. So please, 5 minutes for questions.
No problem. Any question from the audience? Okay, if there are no questions, and then we can close the session. No issue, no problem. Fine. Well, see you tomorrow morning.
Thank you very much. Thank you all for participating, and thank you, Arvind, for organizing this. And see you tomorrow. Bye-bye.